Today we'll be talking about modern cryptography in Java or not getting pwned in 2020, all right? So I'm going to give a little bit of background here. Uh, we're going to be using as inspiration SSS/TLS or the protocol using HTTPS, or as I like to say, what happens when programmers try to use cryptography and cryptographers try to program. So a little story here. And I'd gone to go do a talk about Log4j. And during that time, there was announced during that week, during ApacheCon, was the announcement of the Heartbleed vulnerability in OpenSSL. Now, this affected a ton of production applications, particularly web servers that use HTTPS. It was a fairly when you look at the technical details, it was kind of a fairly obvious bug to a programmer, but not to a cryptographer, let's say, essentially around memory usage. But that's basically kind of what happens when things got tried to get a little fancy from a cryptographer point of view, I guess you might say. This was kind of my first experience of learning that cryptography wasn't infallible, and in fact, might not even be written by people who know how to program all that well. So it was after I started to get a little more interested in cryptography. But isn't it supposed to be secure? I thought this was all mathematically secure. I remember learning in university about how it would take longer than the universe has existed to brute force attack various cryptographic schemes. So how was it that people were figuring out how to break these systems? Well, let me tell you a little bit about myself. So as we mentioned earlier, I'm involved with Log4j and Secretary of Apache, and also recently became Secretary of CJUG. I work on the security team at CloudBees on Jenkins, but I did get interested in security a little bit before I ever started working on it professionally. Now, there was a Heartbleed vulnerability that kind of piqued my interest early on, and then eventually I kind of got into more Java deserialization issues and other things. But in reality, I was kind of interested in this because I'm also a math geek, and I went to college around this type of thing. So how can we make this secure? We have the technology, and in fact, we can totally do this. It's just that we just needed to kind of align the interests of mathematicians and programmers. So in order to do this, we're going to go back and cover three particular concepts of security. And in fact, this is somewhat complementary to our previous talk because we won't be covering some of the cryptography that was touched on by Mercedes. But three concepts that we'll be going over are confidentiality, integrity, and authenticity. So, and in particular, we're going to be kind of talking about encryption and how it's actually used in practice. So confidentiality is the main thing that encryption itself will provide. And that just basically means that third parties or unintended people are unable to understand the message that's being passed between people, right? So it's kind of providing that secrecy, only the secrecy though. There are other two concepts. Integrity is showing that we get something unmodified. We can detect if something was changed in between. So for example, if somebody had modified the contents of a message passed between me and somebody else, I'd be able to tell, or they'd be able to tell based on checking by using some sort of integrity checking algorithm. And then our third concept is actually somewhat related to integrity, kind of builds on top of it, is called authenticity, which essentially means that you can't impersonate someone else. You know that the message you received is authentically from that person that claims to have sent it to you. That's somewhat related to the signature aspect that was used in the JOT tokens earlier. But we will be talking about the symmetric versions of those coming up soon. So ciphers are the cryptographic primitives, so to say, that we use to implement encryption. So ciphers are encryption and decryption algorithms. They complement each other. One does the inverse of the other. They convert a plain text to a ciphertext and in reverse. One of the design constraints that they have too, by the way, besides the confidentiality, is they have to be fast because encryption and decryption is used on the fly constantly for all sorts of things. So there are two main axes that classify ciphers along and how you would end up using them. One is how the key, which is the only thing that we need to keep secret generally for a cipher. A symmetric key or symmetric cipher only uses a single key for both encryption and decryption, whereas an asymmetric cipher uses a pair of keys, a public and private key, that do one or the other operation, that do the opposite operation of each other. So, for example, a symmetric cipher might be used for encrypting the data in a network connection or encrypting a file, whereas the asymmetric cipher might be used for exchanging the key used for symmetric encryption. That's a little bit of a technical detail because asymmetric cryptography tends to increase the size of messages, whereas symmetric cryptography doesn't. So that's kind of, in practice, how it ends up being used. The other classification of ciphers are on what types of data they operate on. The most general type of cipher is a stream cipher. They operate on any length of data, aka a stream of bytes, or stream if you want to get as low level as possible. Whereas a block cipher operates on blocks, typically something like, let's say, 16 bytes or 32 bytes. Small sizes typically similar to the key size. We also have, in Java, though, this is controlled by the confusing class Java. Moment, we have a small code example of how ciphers might be used in Java. So a few little things about this. We are going to be using a secure random number generator. The implementation details of how those work are beyond the scope of this talk, but they are the easiest way to use that in Java is to just use the fairly new-ish method, get instance strong. That'll make sure that you didn't mess anything up. We create a 256-bit key, which is the maximum size for AES here. And we also have to create an IV, which is something that is essentially a non-secret value that's used specific to encrypt a message. It has to be something unique, so we're just going to generate something random. In certain protocols like SSH, we can use a sequential sequence based on networking protocols and whatnot, but essentially the idea is these things have to be unique, and by reusing it, we're actually going to break the encryption. So you'll notice one of the common themes about these crypto APIs is they're extremely fragile. So one of the themes we're going to come to is how can we actually use these APIs without screwing it up so easily? Because as you can see, this is not very straightforward. The code I have here showing both encrypting and decrypting data, and this doesn't even include the greater question of how do we manage keys between different people and things like that. For answers on that, see identity management and various key management solutions that go along with that. So our second security concern was around integrity. And in this case, we have the concept of message digest, or a hash function. So these are mathematical functions that basically take something of an arbitrary length and turn it into something of a fixed length. In this case, that value is called the hash value. So some common examples of hashes you may have heard of are MD5 or SHA-1 or SHA-256 or things like that. We can use these to calculate a value of a message that will change tremendously based on just tiny changes to the message and a couple other related security properties. Basically make it so that the hash itself is a very good indicator of the greater message itself, but just compressed down to this tiny amount. So we can kind of use this to detect whether or not some data had changed or had been tampered with by rechecking a message digest of some data. So for example, in this diagram here, when Alice sends a message to Bob over an insecure channel, Alice can compute the hash value or message digest of her message that she sends to Bob. Bob can also calculate that same hash on it, check the digest, and make sure and see if it's the same. As long as it's the same, they know that the message wasn't tampered with. If it's different, the message was tampered with or it was corrupted through network transit, perhaps. However, maybe a keen observer might notice that, hey, well, what if if there was a person in the middle, a so-called man-in-the-middle attack? Could they change that hash to whatever they wanted it to be? Well, this is where we'll come to that in a moment. This is a quick example of how you might use a message digest in Java. In this case, I'm using SHA-3, which is brand spanking new, not even available in Java 8. So I may notice in these code examples, they're using Java 11, using var syntax and such. This not required, of course. This has been part of Java since at least Java 1.4 or so. Not SHA-3, but crypto APIs have been. But in this case, it's essentially showing that the message digest does not change between invocations. And in fact, it doesn't require a key or anything. So as you'll notice, this is not a secret value. It's sort of just a way to check the integrity of something, right? Now, if you want to actually make sure that the data was not only not changed, but is the data from the person who meant to send it, we can use what's called a message authentication code. What's cool about this is we're basically going to combine the two previous concepts of a message digest and a cipher and use them together to form authenticated message digest or a message authentication code. So this will take a message and it will take a MAC algorithm. MAC algorithms tend to take a hash function and a cipher and kind of combine the two. Now you'll notice this is kind of similar to a signature. This was kind of mentioned earlier. A signature would take an asymmetric algorithm, whereas a MAC would take a symmetric algorithm. But essentially, this allows us to both check the integrity of something, but also check to make sure that the only person who could have decided that the authority to do so, or has the ownership of this key. I will note, not mentioned in the slides here, the primary security difference between a MAC and a signature is a signature also provides non-repudiation, as in if I use a MAC to authenticate a message between me and someone else, only me and that other person can use that code to verify that it was authentic. If I sent that code to somebody else, I could still pretend to be anyone else. They wouldn't have any way of actually verifying. Whereas with a signature, they'd be to use the second half of the key, the public-private key pair, to verify that signature. So that would allow a third party to also check, and that would also mean that I could not say that no, that wasn't me who sent that message because I signed that message with my key that is verifiable by you. So how do we use a MAC? MACs are a little more complicated than message digest, but they're a little simpler than using a cipher. Essentially, they're very similar to the cipher, to the message digest API, except instead of using digest, we're going to use do final, which kind of matches the cipher API a little bit more. But essentially, that's going to initialize with a key. And in this case, I'm using an HMAC SHA-512. So as I mentioned before, they tend to combine a message digest with an encryption algorithm. And in this case, I believe it uses AES. I don't remember specifically about HMAC, I think. But anyway, so that's all fine and dandy. We got some crypto primitives. And as I mentioned earlier, they're all fairly fragile. I mean, you see how there's some very tedious dances you need to do in order to set everything up. So how do we use all that together? And especially, why was that so hard for HTTPS and other various crypto, like network standards, to adopt security properly? Well, this was a question asked also by cryptographers, and the answer they gave us was this concept known as authenticated encryption. Is a little bit stronger than just encryption. Remember, encryption only provides confidentiality, but if we want to provide all three of those concepts together, we kind of need to combine both a cipher and a MAC. And remember, a MAC kind of combined the cipher and the message digest, so now we're just going to take all three together. I originally had a little code sample to kind of show you what that might look like manually, but you know what? I think that just does more harm than good, because I could just point to the problems in TLS and the problems historically from SSH and other various protocols that also screwed it up. So why bother? Let's just use the correct API. That is called Authenticated Encryption with Associated Data, or AEAD. So this was standardized in RFC. I don't remember which, but it's a 4-digit RFC, as most of them are. And it essentially defined a standardized API for us programmers to use cryptography without messing it up. Now, that sounds like it should have been a design goal back in, I don't know, maybe the 1950s or something, before digital computers were like widespread and before programming was a profession. But you know what? All right, they waited until the 21st century to actually tell us how to use cryptography. And you know what? I blame there's a legal history behind that, but that is no longer a problem. So now we have to make cryptography accessible for everyone. So essentially what authenticated encryption does is it will first encrypt data, and then it will take a message authentication code of the encrypted data and use that as a way to check the data. This prevents multiple different, somewhat esoteric, but devastating cryptographic attacks that are extremely hard to describe without another hour of details. But so we're going to kind of hand wave away from that and just say that if the encrypted data is not authenticated, how do we know that the data wasn't changed in transit? And if we don't have that guarantee, then that will allow attackers to start doing fancy things. So using AEAD, if we actually compared this to the previous slide of how to use just plain encryption, you'll notice that it's almost exactly the same API. The only difference here in this particular use case, I'm using a particular authenticated encryption variant called AES/GCM. Now, this is one of the more common standardized forms of AEAD. It is, I would assume it's the most popular one, or the second most popular one. And it typically has hardware support too. So if you're worried about performance, don't be. So in order to implement AES GCM, there's one small difference between that IV from earlier was that they also specify the size of the message authentication code, or the tag, authentication tag as they call it in GCM. In this case, we'll just use the largest size, which is 128 bits. But essentially in this case, we can do two things in the same API now. We're both able to encrypt and authenticate data, which is what we would normally do. But then sometimes there's data that we need to send and provide an authenticity check, but we can't encrypt it. For example, in the IPsec protocol commonly used for VPN connections, in order to route data over the internet, routers still need to read IP address headers of IP packets. Whereas IPsec, one of the modes of IPsec is to encapsulate all of your network data in encrypted packets. Now, if you kind of look at the sort of contradiction here, you'll note that your network packets include the IP address of where you're sending data to or getting data from. So it sort of sounds like a catch-22 of how the hell am I supposed to send an encrypted packet if I still need to have some of it unencrypted? Well, in the AEAD interface, that is considered authenticated additional data, or additional authenticated data, or AAD essentially. And using this update AAD method that was added in Java, this gives us an additional way to sort of add header data, so to say, to a message that is getting encrypted, but while not encrypting that header data. This will make it so that if that header data is modified, it will still be detectable because it's still authenticated, it's just not encrypted. This allows us to keep everything secure without compromising without compromising our security goals, while still maintaining compatibility with various applications. So coming from that, I'd like to kind of leave you with some do's and don'ts of how we can actually use cryptography now that you have a gist of the concepts here. So on the do side, I'd like to go with some things that maybe that aren't very common knowledge too. One thing is, make sure to use authenticated encryption now, especially now that I've shown you that it's actually a fairly trivial change if you're already using encryption to use authenticated encryption rather than unauthenticated. As I said, it's a fairly trivial change. It's not going to affect your performance too much, particularly because CPUs include hardware instructions that support AES and GCM. And there is also an alternative popular algorithm called SHA-20 Poly 1305, which is slightly newer than AES GCM, which was designed with modern CPUs in mind. Essentially, the algorithm is, instead of being designed from a mathematician's point of view, it's kind of designed from the point of view of a hardware engineer of how am I going to actually make this work properly without leaking information, but also being fast. SHA-20 is a pretty cool algorithm that implements that concept. From what I understand, it may not be as fast as AES GCM when you have hardware support for it, though. So I would recommend benchmarking if it actually matters to you. As I mentioned earlier, make sure to never reuse IVs or nonces. That these are slightly similar to keys, but the keys are able to be reused a certain number of times. An IV or nonce is not similar. In fact, I kind of prefer the term nonce to IV because the definition of a nonce is something that is only used once. And in fact, it's a very similar concept that we use in other various authentication mechanisms that would use that term. It always means use once. IV just sounds like some weird acronym that, again, just like most crypto things, is just opaque. And then finally, on the do's, where possible, try to just use a higher level crypto API or protocol or library that does things for you. For example, I found an interesting library from Google called Tink, which provides various high level cryptographic operations, such as AEAD and signature operations, all the other various things that I've talked about, except without having to have 15 or 20 lines of Java code. And instead, they'll have very simplified forms that you can do it in a single line. And it might actually be simpler than the equivalent Python code. Isn't that cool? Another similar library I found is called JavaScript. I think this has existed longer, but it's another similar library for kind of giving a higher level API over various cryptographic primitives. Not linked here, though, is another library I found after I put slides. Some chat protocols such as Matrix, which provide some sort of high-level crypto operations to use in your own custom protocols, so that you can create something secure using high performance and high security cryptography, but without having to go and spend several months reading documentation and not messing things up. So on the don'ts, though, this is the fun part, because it's easier to mess things up in cryptography than it is to get it right. And that's one of the goals here of trying to evangelize these AEAD and other more modern ways of using encryption, is use the correct way of doing it so that there's no way to do it wrong. So in that case, here's some lessons that we've learned, especially some things over the past decade. For example, don't use old insecure ciphers for encrypting data. I will note, I specifically say encrypt data, not decrypt data, because sometimes backwards compatibility will be an issue and you'll have to decrypt old data. I'm not going to say don't do that, because sometimes you do. Just don't continue to use old ciphers for new things. What are ciphers? They're things like DES or 3DES as well. RC4, which was being recommended up till a few years ago. As a matter of fact, one of the HTTPS security vulnerabilities discovered in the past few years, one of the workarounds was to use RC4, until about a year later, when cryptographers showed that RC4 was a travesty of a cryptographic algorithm that could be hacked from here to Timbuktu. So one lesson there, don't use RC4. Another one, don't use export-grade cryptography. This is a relic of the 1990s, from back when cryptography was considered as dangerous as a nuclear warhead. Clearly, it's not. And in fact, it is widespread, and especially because open source software is widespread around cryptography, it is no longer has such onerous legal restrictions around use. One of those restrictions back in the day was key sizes for cryptography that was exported from the United States to other countries would have to be reduced to a size that was effectively small enough that the NSA was able to hack it. That's turned out to actually be a problem, especially now in 2020, when everyone else has the same computing power that the NSA had back in the 90s, and everyone else also hack it. That was also used in certain HTTPS attacks to downgrade the protocol to force it into using these insecure protocols. So I'll note, with a caveat to that, don't use old ciphers for encrypting data. Also, don't use it for decrypting data in a situation where there is some sort of handshake involved that allows an attacker to choose which cipher is allowed. Another thing related to that is, don't worry too much about performance. I know that this was a much bigger problem, let's say 20 years ago, maybe even 10 years ago, but definitely not now. As I said, CPUs actually have assembler instructions for AES. Take a look. It's fairly interesting. There's even a fun one about adding and multiplying numbers in a finite Galois field, and you'll be like, what does that even mean? Why is there a processor instruction for just this one thing? And it turns out it's to help implement GCM faster. Cool, right? So that your CPU can actually do this for you. And when I say don't worry about performance, I really mean it. The CPU in your credit card can handle AES. I think your application can handle it too. And as I said before, stop assuming that exporting cryptography is illegal. One of the reasons I actually got reignited in cryptography originally was one day while working on Jenkins, I found as a comment in code, commented above an initialization of an AES key. It said limited to 128 bits because of stupid US export control restrictions. I spent a couple hours after that researching and finding out that that was no longer valid for over 10 years, but nobody had bothered to go back and update that because cryptography is hard. And once you get your first bug report in CVE around misusing cryptography, you kind of lose the, you kind of lose that desire to ever touch cryptography in a production application ever again. So unless you want to be the person who gets blamed for, for some crazy data breach beyond your pay grade. Well, you know what? I'm trying to say, don't get too intimidated by cryptography because cryptographers have been doing a lot of work towards actually making these easier to use. And one of those big things is authentication or using encryption. Even if you're not using encryption directly, I'd recommend if you're using it indirectly through things like SSH or HTTPS servers or even a VPN connection, maybe you want to take a look at the ciphers that are enabled in your thing and make sure that they're still not using RC4 or 3DES or other old cipher mechanisms. For further reading, I'd take a look at the TLS 1.3 standard, which kind of goes over some of the reasoning behind why a lot of these old ciphers have been all deprecated. So with that, I would like to take any questions you have about anything I've gone over. Also, anything I didn't go over, I can possibly answer, but yeah.
Actually, I'm wondering for like with the cloud, is there anything like of applying those techniques would be like different, in a cloud environment?
Oh yes. So in the cloud environment, one of the big changes I would say differences between the cloud environment and a more traditional environment has to revolve around key management. And interestingly enough, that was briefly touched on earlier by Mercedes about in identity management platforms, you can oftentimes attach various cryptographic keys to users or groups or things like that. In the cloud, the main thing you're going to be doing is, compared to more traditional servers, is things are much more ephemeral in the cloud. So, for example, one of the I'd say complexities, I guess you might say, of using cryptography traditionally even is distributing your key various things that need them, and that gets a little more complicated in the cloud because now things aren't always staying where you expected them. So for example, when you're using certificates like HTTPS certificates, they might involve domain names or various things. Previously, like back in the old days of SSL, this basically kind of one certificate to one IP address was sort of like a one-to-one mapping. And that doesn't exactly map well to the cloud when you have an IP address corresponding to a load balancer that goes behind to multiple real machines in the background. That was various things like that were upgraded over time with TLS certificates. But in order to actually keep now, like that might still be simple to do. Like let's say you're just a single Apache or Nginx server or something to put your HTTPS certificate in. But with the in a cloud environment, you probably have a ton of different microservices that might need their own TLS certificates in order to talk to each other or things like that. So the big difference there would be using some sort of key management solution that allows applications to make API calls or sort of have mounted on them when they're running the various secrets they need in order to make the cryptographic communications.
Another issue that came up in cloud environments was that within Linux, with dev/random, that was generated by hardware interrupts, and that was used to create random numbers, which are used in these cryptographic algorithms. That was fixed in many of the hypervisors. I think Hyper-V was one of the earliest ones to do that. Or no, Zen was one of the earliest ones to do that. They'd have hardware, they'd have drivers from the hypervisor to help assist in the number generation for the host.
No, actually, for use cases like that, I don't know how many people actually use this. I bought one a while back, but there's this device called the One RNG. It's like this open hardware thing. It's like a hardware random number generator that will take noise from the environment, quantum type noise, and translate that into seed values that feeds into the RNG. That can kind of help in scenarios where you have a ton of depleting the entropy of your random number generator. Now on the more modern front, I have seen that some operating systems, like I think Linux has even switched to this, but I've definitely seen this in some of the BSDs, have actually switched their random number generator implementations to use Cha-Cha-20, the cipher itself, because the way a stream cipher tends to work is they basically, using a key and an IV, it will generate a, let's call it infinite, but it's not infinite. There's a limit. It's called an infinite stream of random data, of pseudo-random data. And then that data is combined with your message, and that becomes the encrypted data. So that stream of pseudo-random data, it also works as a random number generator. And not only just an RNG, but a cryptographically secure random number generator, as long as it's seeded securely. So you still end up with having to periodically reseed the random number generator. It's just my understanding that by using this algorithm, they get a much longer period and are able to work better in a cloud environment where you have a lot of things depleting the random data. Now, I don't know enough about the math to say whether or not that just means the NSA took over somebody else that used to be fighting the man, and now all of a sudden he's working for the man. I don't know, but if we trust that algorithm to work right, it should make it. It should kind of reduce some of the performance issues too, because there's the related issue here that you bring for is that dev random / dev u random in Linux. Having two different devices that emit random data. And the main difference, at least in Linux, being that dev random will wait to gather more entropy from various hardware sources to reseed that random number generator, whereas the dev u random won't. If it has run out of entropy, it'll just keep running the random number generator algorithm. Now that would, in some platforms, as long as that the algorithm that they use for random number generation is cryptographically secure, that works out fine. But I'd imagine historically that wasn't always the case. So that is also something to keep in mind when using dev random or dev u random in applications. For when you're using for cryptographic applications, it is typically better to use dev random. And probably within the past few years. So I mean, we're talking Linux 4.8. Dev random shouldn't even have too much blocking, if any, at this point as it is. It kind of does it asynchronously, refilling your data. So again, on the whole performance aspect, a lot of this stuff, because of this is also somewhat of a chicken and egg issue too, where that some of the performance problems of cryptography were only performance problems because not enough people were using cryptography and there wasn't enough demand to solve that problem. Well, now that everybody's using HTTPS everywhere and cryptography for everything, the demand for hardware solutions to fix this exploded, and now it's so widespread that, like I mentioned earlier, your credit card can perform AES operations.
Hi, Matt. This is Jay. Yeah. We use API key quite a lot at work, and we're using OpenSSL to generate those. What is your advice with your recommendation? Is there any other better way
For generating random data?
or is there I mean advanced version of the OpenSSL?
Oh, okay. So OpenSSL would support these AEAD. These are just one of the types of APIs that would be provided by a cryptography library. So it's like one of the things I've even noticed, like one of the few times I actually tried looking at OpenSSL's actual API and seeing that it basically exposes every tiny little detail that it possibly can. And you may note just the samples of Java code I show already expose a tremendous amount of internal detail about cryptographic primitives that usually as a programmer I don't really care about. And when you expose it to me as a programmer, I'm more likely to mess it up. Whereas with AEAD, it sort of kind of reduced the API surface level to something that you can't really misuse. Like for example, one of the, like there are various optimizations around sort of preventing various misuses of cryptography. So for example, that IV reuse problem I mentioned earlier, the way AEAD algorithms are described is that the algorithm should reject an IV that it's already used for the same key. Or for example, when decrypting authenticated data, if that MAC or authentication tag is not valid, the algorithm should refuse the data. So, for example, in Java, it will throw an exception, and your byte array or stream or whatever your interface you're using at the time will remain encrypted and unchanged. Now, from a API key standpoint, the similarity here would generally be making sure to be using the same cryptographically secure random number generation that you'd be using to generate keys, whether that's like a secret key for cryptography or if it's an API key for use by a client. Because API keys, you also similarly wouldn't want them to be predictable or reverse engineerable because there might be some sensitive information attached to that. If you really want to take an API key though and take it to the next level, really the best thing to do is kind of follow the JOT token, the JWT's idea, and use and essentially you'd be taking that data that's in that I forgot, was it basically the payload data, I forget, was that the claims, I think, and inside there, that data you would essentially encrypt. And not just with the signature, but maybe you'd end up encrypting that data too if you didn't want it to be seen. But then you'd be able to use that way. Your server would be able to check that data afterward. It allows you to offload more of the information to the client at that point in a situation where you can still verify that it was a trustable thing, essentially. So I guess the idea here being that when you use authenticated encryption, it allows you to do more things in an untrusted environment. But do note that when I say an untrusted environment, I mean when Alice talks to Bob, the trusted environment is Alice and Bob trust each other, not Alice and Bob don't trust each other. An example of misuse of authenticated encryption is with copy protection, or DRM. This will typically use encryption or authenticated encryption to try and encrypt a message from Alice to Bob to prevent Eve from reading the message, right? That's how encryption would normally work. But in the case of copy protection, Alice sending the message to Bob and Eve are the same person, because the person trying to eavesdrop and the person receiving the message are the same person. That's not how cryptography works. Cryptography can't provide that. So in that sense, we can only provide sort of like these very security guarantees based on existing trust relationships types of ideas. So let's say, so you wouldn't be able to use this, for example, to encrypt some data and then send it to your iOS app and then expect it to be safe if the iOS app has to decrypt the data too. It's like, but you can use that to have a secure line of communication between the app and the server, for example. More questions?
Any more questions? Sorry. I guess if not, then yeah, then I think this is good. But again, thank you so much, Matt. It's a great presentation.